Lesson 422, graphing rational functions. So in the previous lesson, we graphed rational functions in this graphing form or transformational form, right? However, not all functions can be written in that form. So today we're going to graph and rewrite equations of rational functions in different forms and learn how to describe discontinuities and in behavior. So this first question here, 64, says, who's the greatest? So when deciding on in behavior of a polynomial function, which term really matters? So for each polynomial function, analyze the terms, right, as x approaches infinity and negative infinity. And we're going to do this by creating the tables. So there's tables here, and you can see they've kind of already done this for us. But what happens then when we plug into this polynomial function, and which term really relates to how the graph ends? Well, if you're looking at this, right, and you plug in 100 here, 100 squared is going to be 10,000. Well, 100 times 4 is 400, and then negative 12. So you can see that, you know, as this number gets squared, right, this number is going to be really, really large. So this x squared number or x squared term is what's going to affect it the most. And then the same over here, right? Even if it's negative and we square it, it's still going to get really, really large. Whereas just times 4 or that negative 12 is not going to affect it as much. So what we learn from this, like even in this function here, right, the largest degree or the largest exponent, is the term that's going to affect the graph the most. So we're talking about x cubed there being the term that affects it. So 65 here, what happens when polynomials are divided? So the same idea, if we know that largest exponent's what affects it the most, then what happens then? So if we're looking here, you know, at this first one, right? So if we have x squared minus 12 and x cubed minus x squared, this first term's really what's going to affect it. So we're really just concerned, you know, when we're concerned with in behavior, we're concerned with the largest exponent over the largest exponent. Well, when you plug in 100, right, you're going to get this. And then down here, you're going to get a massive number, right? So just a really, really big number. So what happens here, right, is the idea of you're going to get a small number over a large number. Okay, well, what happens when you do that is, you know, 1 over 100, right? So you're approaching 0. Right, because this is 0.001. So you're approaching, 0.01, but you're approaching 0, right? That's the whole idea. When you have a large number on the bottom, you're approaching 0. Okay, same thing on B, right? Again, the term that's going to affect it, x squared, x cubed, you're going to approach 0. Okay, look at C. So here, the term that's going to affect it, right, is x squared over x squared. Well, you're going to end up with the same number over the same number. So this becomes a leading coefficient ratio. So whatever you plug in here, you're going to approach 3 over negative 1 or negative 3 is what you're approaching, right? And then here, when you have x cubed over x squared, you're going to have a large number over a small number. So when it's really, really large, you're going to approach infinity, or it could be negative infinity. So it could be either one there, depending on what you're plugging in, if it's really large or really small. So as we're talking about in behavior, this is how we do this. Well, this actually is the same rules that apply to our horizontal asymptotes. So we're either approaching that horizontal asymptote, or we don't have one. We're approaching negative infinity or positive infinity, right? So here's kind of the rules here, right? If you have a rational function, right, to some power, and m is bigger than n, right? So the exponent up top is bigger than the exponent at the bottom, there's no horizontal asymptote, okay? If they're the same, then it's the leading coefficient ratio. So that means, that's this example here, right, that we're talking about. And then if m is smaller than n, then our horizontal asymptote is at y equals 0. Okay, we're always approaching that 0. So that's in behavior, but it's also horizontal asymptote rules. Okay, so now let's look at the other thing. So we have this function, right, and we have this function. And so it says, for what values of x is each term undefined? So for x values, we're talking about what could x not be? Well, again, we can't divide by 0 in math. So if we're looking at this, right, for f of x, we have x squared plus 5x plus 6 over x plus 1. For the second one, we have x squared plus 5x plus 6 over x plus 2. Okay, so what's going to make this 0? Well, if we talk about this, what's going to make this 0? Can't divide by it, right? So we're talking about x cannot be -1, x cannot be -2, right? And so that is where our issues lie. Okay, well, now we need to look at what happens when we graph these. Okay, so let's go to Desmos and let's graph these. And so I'll go to Desmos, and then I'll come back and I'll start the second video from Desmos of where this happens.